And welcome to our 8th session of our Discrete Diffusion reading group. And today we're going to present the diffusion duality. This paper was published last year at ICML, and today I'll be co-presenting this with Justin and Zhihan. And now this might be, slightly a bit on the older side, but I thought we should cover this paper now because in the next few weeks we're going to release at least 2 papers where we make the argument that this uniform state discrete diffusion models are the future for designing diffusion language models, and it's not mass diffusion. So I thought now is a good time to cover this paper so that it's easier for people to follow the subsequent papers that will be released soon. Okay. Okay, so, like recently, diffusion language models are getting a lot of traction with Google's Gemini diffusion, ByteDance's Seed diffusion, and Inception Labs' Mercury Coder. Their impact has reached mainstream media with Forbes and Fortune publishing articles that highlight their effectiveness. And so there's a lot of excitement surrounding diffusion LLMs, and rightfully so. These models are not only effective, but also significantly faster than their autoregressive counterparts. But discrete diffusion is fairly new, and there still are a lot of open questions that are unanswered. So Gaussian diffusion models for image and video generation are quite mature. They are supported by a rich set of techniques for efficient training and inference. For example, when it comes to like samplers, there are numerous choices, right? You have your ancestral sampler as it was proposed in DDPM, but later on people found more interesting samplers such as the ones proposed in EDM that use second order terms, or even like consistency models that train these models or allow these models to generate samples in few steps, right? Then again, like people were able to use the underlying PFOD to design deterministic sampler. Furthermore, like you have other samplers like mostly rely on the score formulation of your Gaussian diffusion models. Similarly, for effective training, like Gaussian diffusion is well studied. You have numerous techniques, for example, like learning the noise schedule as was proposed in the variational diffusion models paper, and also like in elucidating the design space of diffusion models, these authors propose many interesting parameterizations and training recipes to train these models. Similarly, when it comes to parameterizing the denoising model, nobody uses mean parameterization. That is, given a noisy sample, a Gaussian, like a noisy image, nobody predicts the clean, you don't train the denoising model to predict the clean sample X. But people found that if you force the model to predict the added noise, you end up with a much better trained model. And later, people came up with something called velocity parameterization, where you force the denoising model to learn the clean signal X in the initial stages of diffusion, and in the later stages of diffusion, where there's more noise, you force the model to train the added noise. So, like the point that I'm trying to drive here is Gaussian diffusion has existed for a while. People have studied this a lot, and its field is much mature than the discrete diffusion models, which probably got attention in mid 2024 with papers like SET and MDLM. And if you think about it, in the recent years, the best way, like mean parameterization is still the dominant form. Okay, I think somebody is unmuted. Justin, can you find them and mute them? Okay, never mind. Okay, so we have mean parameterization, and then when it comes to samplers as well, ancestral sampling is the go-to way of sampling from these models. We don't have various choices as we have for Gaussian diffusion models, right? And also, like when it comes to improved training recipes, the one proposed in the blog diffusion paper where we suggested clipping the noise schedule, that is probably that is probably the go-to way of reducing the training variance. Like all the fancy techniques that exist for Gaussian diffusion, they just simply don't apply to discrete diffusion, right? So now let's take a look at the timeline of Gaussian diffusion models. When they were first proposed in 2020, generating let's say, a 256 by 256 image took thousands of sampling steps, maybe in the order of like 5,000, right? And over the next few years, people figured out algorithms to speed up the sampling process, mostly distillation algorithms. For example, with consistency models and inductive moment matching, which was published at ICML last year, the authors were able to get really competitive performance with GANs in few sampling steps. Like maybe if you do 3 or 4 denoising steps, you're able to get really good quality samples. It's only like last week, I believe, the drifting model paper was able to achieve or match the sample quality of a GAN using just a single step, which is a huge achievement. And if you think about it, it took 6 years. It took us 6 years. I mean, all this probably thousands of papers were written, and it took us 6 years to go from to reduce the number of sampling steps from thousands to 1, right? So in this paper, we asked this question: can we design a discrete diffusion framework that enables the transfer of this advanced training and sampling techniques from the Gaussian domain to the discrete domain, right? This is the first question. And the second question is, how do we enable few-step generation in diffusion language models? Because when this paper was written, there were no algorithms that allowed few-step generation in these models. By few-step generation, what I specifically mean is the goal is to generate 1,000 tokens, let's say 1,000 words. Can you generate 1,000 words in, let's say, 8 denoising steps or 16 denoising steps? I think the only paper that came close was Justin's paper, where he was able to show that like using mass diffusion models, you can definitely reduce the number of sampling steps in the range of hundreds. But when it comes to when it came to few-step generation, mass diffusion just did not work. Okay. Now some background. So we all know how autoregressive models work. Like you predict the first word, and then you predict the next word, condition on the first word, so on and so forth, right? So you end up generating words in a left-right fashion. To generate 11 words or tokens, you need 11 steps of generation. Again, for mass diffusion as well, I'm not going to spend a lot of time here. With mass diffusion, you start with a sequence of all blind tokens, and you fill in words randomly, right? And at every step of generation, you're allowed to predict more than 1 words. So naturally, if you want to generate 11 words, you can probably get away with just 7 steps of generation. And mass diffusion is currently the most dominant form of diffusion language modeling, especially it is actively used by wide dense seed diffusion. And nobody knows what the closed source models, frontier LLM, diffusion LLMs are using, but the hope is that, probably it's mass diffusion. The main challenge with mass diffusion models is that the quality degrades a lot when you reduce the number of sampling steps drastically. So if you want to generate, let's say, 11 words in just let's say 4 steps, what happens is as you predict a lot of words at every denoising step, you end up with a lot of incorrectly predicted words. And if you notice, once you predict a word, the predicted word does not change, right? So that sort of leads to this catastrophic failure during sample generation, especially in the few-step regime. So for the purposes of this talk, we're going to focus on this largely overlooked class of algorithms called uniform state discrete diffusion. This was initially proposed in Austin et al. Their seminal paper, and these algorithms have been around for a while, but these methods simply just don't work. So the way these models work is, well, you first start with a random initialization of a sentence. Then you have a denoising transformer that updates the words. We'll look into the training and sampling recipe in detail in the later part of this talk. But for now, let's look at the generation. So you have a denoising transformer that updates the words, and the underlined words are the updated words. As you keep on generating from the model is able to refine its earlier prediction, and if and the hope is that with just a few steps of denoising, you can generate the final sentence. The hypothesis is this kind of model supports self-correction, unlike mass diffusion models, which is why we hypothesize that this kind of model should be suitable for few-step generation, right? But not yet, as I mentioned before, these models underperform compared to mass diffusion models. Okay, so the key contributions of this paper. In the next few slides, I'll demonstrate that this class of uniform state discrete diffusion methods or algorithms that emerge from underlying Gaussian diffusion processes. Then we'll take a closer look at two of the implications. The first one is faster training of these models via curriculum learning, something that Justin will present. And the next one is faster samplers using distillation that Zhihan will present. Okay, so in the next few slides, we're going to do a deep dive on the theory. It's going to be mathematical and it'll get fairly technical, but bear with me. Okay, so in this talk, we're going to represent sentences using colored boxes shown at the top. So you have the clean sentence X at the top here, which represents this sentence that we saw in the earlier in the presentation. And we're going to use this faded color boxes to represent corrupt tokens, right? And at the bottom, you see the fully corrupt version of the clean sentence X. Now, I must clarify that the faded color does not mean these are any special tokens. So you have a vocabulary set, which consists of all possible words. And the corrupt tokens are simply, when I say a corrupt token, what I mean is a token drawn randomly from that vocabulary set, right? Let's say you had the word like Earth here. Earth transitions to moon, and the word moon was drawn from your vocabulary set that had, I don't know, tens of thousands of words. If you notice, you start with the clean sentence X, and as the diffusion process goes on, you recursively corrupt your previous sample until everything, all the tokens are corrupt. Okay, so to reiterate, you have your clean sentence X at the top of the slide, fully corrupt version at the very bottom. Every token here is drawn from this uniform categorical distribution. So this is a vector. So this distribution denotes or assigns equal probability to every token in your vocab set. So if you have 1,000 words, every word is chosen. Like the probability of choosing any word is 1/1,000. This is represented in a vector manner. So, okay, now you have a function Q that goes down in time and it corrupts your training signal X. And you have a function P theta that goes up and tries to recover the corruption done by the function Q. Our goal is to learn this function P theta. So I'll present how to train the function P theta first, and then I'll show you how to sample from the model P theta. So effectively, after you have a denoising function P theta parameterized by a transformer with parameters theta, you would simply start from the random sample at the bottom and use the function P theta to denoise it until you end up with a clean sentence X. Okay, now let's try to understand how the function Q corrupts the clean signal X into this noisy sequence ZT. We're going to represent your intermediate noisy samples using ZT. Okay, first, we define a function alpha t. So alpha t varies from 1 to 0. When alpha t is 1, you have your clean sentence X. When alpha t is 0, you have this fully noisy sequence. And to get ZT, you flip a coin based on alpha t. If you get a heads with a chat, like let's say if you get a heads, you retain every token. You basically toss a coin for every token, and you retain it with probability alpha t, and for the remainder of the tokens, you simply draw a token from your bag of words and you replace it randomly, right? So that's how you get a sample ZT. Now, concisely, these two steps can be written as a single expression. So you have this. So the intermediate marginal for every token is essentially a linear combination of your one hot vector of the token and the prior distribution. So this functional form is very important. Keep this form in mind because this functional form plays a very key role in establishing the duality between the discrete diffusion and Gaussian diffusion. But the only takeaway here is that this sampling of this sampling process can be precisely written in a single functional form as shown here. Okay. Now to train the model, first we define a transformer which has bidirectional attention. So effectively, this transformer takes in the noisy sequence ZT and tries to predict or reconstruct your clean signal X. If you notice, this transformer is also conditioned on the time step T, which is very common in Gaussian diffusion models, but not so common in mass diffusion models. I mean, the intuition is this, right? Like in mass diffusion models, your number of mass tokens tell the model how many the corruption level, and but there is no good way of doing so in uniform state diffusion or even Gaussian diffusion. That's why empirically people find it to help when you condition your denoising transformer on the time step T, right? Now, at the top, what we show is the training formula for uniform state diffusion models. Again, the exact functional form is very irrelevant, and you should probably ignore it. I'm showing it just for the sake of completeness, right? So let's take a quick look at it. So this equation here has an expectation over time step T, which means that you need to train your denoising model on numerous corruption levels. And the second thing is, in the paper, we showed that if you train your model using this functional form, it lowers the training variance than the previous objectives that were used to train those models. That is the only takeaway from the slide. And if you take a closer look at this equation, you'll see that like you're forcing the model, like these expressions force the denoising transformer to predict the clean signal X, like given ZT. Now you may ask, what if we train this transformer with cross entropy loss instead of this ugly looking formula? I mean, you could do that, but it doesn't work for whatever reason, for reasons that I don't understand. But we did try training the model with a simple cross entropy loss, but we got subpar performance. Okay, now let's take a look. Like after you train this model, let's see how you sample from the model. So it has like 3 steps involved. The very first step is you toss a coin and you compute this probability. What is this probability? It's like just nobody knows. I mean, when it'll become obvious in the next few slides. But like you toss a coin, and if you get a heads with this probability, you toss a coin for every token position, and if you get a heads, you you sample the token from this x theta L, which is the output distribution of your transformer, right? In the second step, for the remainder of the tokens, what you do is you toss a coin again, and if you get a heads, you would draw a token randomly from your vocab set. Like, for example, these tokens were randomly drawn from your vocab set. And the third step is, for the remainder of the tokens, you simply copy the input to the output, right? This is how sampling works in uniform state diffusion. And concisely, this can be written in this manner. So you get this equation when this really, like uniform state diffusion is a Markovian process. So when you use Bayes' rule, you end up with this update formula. And what I showed in the earlier slides was a more intuitive interpretation of this formula. In practice, what you do is you have a noisy sample ZT, you feed it into the transformer, you get some x theta, which is a distribution over the clean tokens x, and then you sample every token from this distribution. And this happens for, you have this formula for every token position, and then you sample a token from this distribution, and that's how you end up with ZS. Okay, now let's do something funky with this one hot vector. So let's say you have a clean. Okay, for simplicity, we're gonna consider the single token case when X is a single token. Let's say your word is cat, right? Now we just discussed in the previous slide how to define a discrete diffusion process, specifically a uniform state discrete diffusion process on your clean signal X. Now what we're gonna do is we represent the cat as a real valued vector, as a real valued one hot vector. And then we're going to define a Gaussian diffusion process. So WT represents the intermediate latent for the Gaussian diffusion process. And the process terminates with a prior distribution, which is a normal distribution, 0 mean and 1 standard deviation. And K here is the vocab size, right? In this example, your vocab size is, let's say, 4. So we define a Gaussian diffusion process. The intermediate marginal for the Gaussian diffusion process is simply this. This is the variance preserving formula for a Gaussian diffusion. And this vector here is essentially, you multiply this one hot vector with this alpha t tilde. So alpha t tilde, again, is the signal level, which varies from 1 to 0, 1 representing clean signal X, 0 representing W1, which is a sample from the normal distribution. So this real valued vector here is essentially, you scale the word, like the one hot vector of cat, and then you add some Gaussian noise across every index with this variance. Similarly, this represents a sample of W1. This is like a sample drawn from the normal distribution. Now, something interesting happens. One can potentially take an argmax. So argmax is an operation which, given any real valued vector, it returns a one hot vector. So if you were to take an argmax of this real valued vector, you end up with this one hot vector. So if you see there's this one here corresponds to the index of maximum entry in this vector, right? So if you take argmax of this vector and this vector, what you see is you recover a one hot vector, and that one hot vector corresponds to some word in the vocabulary, right? So now the interesting thing is this. You defined a Gaussian diffusion process here, but if you were to look at the argmaxes of all the real valued vector in this Gaussian diffusion trajectory, you would end up with some latents that might correspond, that look very similar to the samples of a uniform state discrete diffusion process. So if you were to define a uniform state discrete diffusion process in the word cat, you start with the word cat, which would transition to, let's say, dog, which would later transition to the word horse, right? So this observation like motivates the remainder of the talk. So now the question is, are these two processes related in any way? Is there any relation or any fundamental relation between the uniform state diffusion process and the Gaussian diffusion process? And the answer is yes. So in the paper, what we were able to show that, when you define a Gaussian diffusion process, you would end up with intermediate marginals such as this. And when you apply a push forward, an argmax push forward on this distribution, you end up with a categorical distribution that looks like this. Now, what does a push forward mean? So push forward means like push forward is an operation that you apply on a probability distribution. The way this works is, let's say you have a distribution defined as this, right? So you draw numerous samples from this distribution and you apply some transformation, let's say an argmax. So to get this distribution, what I need to do is sample numerous Gaussian latents from this distribution here, take an argmax, and if I were to take argmax of like infinitely many samples and average them over, you end up with a distribution. The distribution of the discretized latent would look like this. So in the paper, we were able to show that when you apply argmax push forward, it transforms the k-dimensional Gaussian distribution into a categorical distribution with k categories. And that particular distribution has this functional form. And if you remember, this functional form corresponds to the intermediate marginals of the uniform state diffusion process. Recall that in the previous slides, we had some term alpha t, and the intermediate marginals of the USDMs had the form alpha tx plus 1 minus alpha t times 1 over k. Now here, instead of alpha t, you have this other term appearing, tau of alpha t tilde. So alpha t tilde is the signal level of the Gaussian diffusion process, and tau is the diffusion transformation operator. So this is an integral. Again, like the functional form of tau is not very important. What this equation conveys is that you can transform alpha t tilde to the equivalent alpha t in the discrete diffusion space, and like that argmax transforms alpha t tilde to tau of alpha t tilde, which is the alpha t equivalent in the discrete diffusion space, and using that alpha t and that argmax also transforms the Gaussian latent to a discrete latent, and finally argmax transforms the marginals, the Gaussian marginal, to a discrete diffusion marginal. Okay. Now, now the time evolution of this marginal as well follows the time evolution of standard uniform state discrete diffusion process. So it's not just the marginals, but also the time evolution of the marginals aligns with that of the uniform state discrete diffusion process. Now there could be some misconceptions surrounding discretizing the Gaussian trajectory. So a couple of slides ago, I said the main motivation for this work was that, I had this observation where you start with a one-hot vector, define a Gaussian diffusion process, and then you take an argmax of those latents, right? You end up with latents that may resemble a discrete diffusion process. While that motivated this entire work, but mathematically, in the paper, we show that if you take the argmax of the latents and then you were to plot all the latents, the discretized latent might not follow a discrete diffusion process, and that only the marginals align. But if you were to look at the discretized Gaussian diffusion trajectories, they don't correspond to a discrete diffusion process. Like in the paper, we show it through analyzing the transition kernels of Gaussian diffusion and discrete diffusion. It's not very important, but something to keep in mind. Okay, the next thing is the samplers, right? So this is very interesting. So let's say you define a denoiser in the Gaussian space, like PT theta bar, let's say. So you have your you have a denoising transformer that takes in Gaussian latents and tries to predict the clean sentence X. So the denoising function and p bar t theta is effectively the denoising function for Gaussian diffusion. In the paper, we show that there always exists an equivalent discrete diffusion process whose marginals align with the push forward of the Gaussian marginals. So imagine this: you start with this normal distribution, and you have this denoising function. You plot all the intermediate Gaussian marginals for this denoising function, Gaussian denoising function. And when you take the argmax, when you apply the argmax push forward to those Gaussian distributions, you would end up with some categorical distribution, right? And all I'm trying to say is there always exists a reverse denoising function in the discrete diffusion space for which the marginals align. And in the paper, we basically show that in fact, the reverse discrete diffusion process takes this functional form. Now, this may be a lot to absorb, but also it's worth spending some time on this because at the end of the talk, when I talk about future works, both the things that I'm going to propose heavily rely on this, right? So, okay, what does it say? So you have p bar theta s given t, right? So this is your transition kernel in the Gaussian diffusion space. It effectively, I mean, given any WT, a Gaussian latent, this thing defines a distribution over your less noisy vector WS, right? Okay, now our goal, the goal of this slide is to say that given a discrete noisy sample ZT, how do I get a distribution over ZS? That's all we're trying to achieve. And I'm trying to show you this equation, which says that, which defines this discrete diffusion transition kernel in terms of Gaussian diffusion reverse transition kernel, right? So, okay, so now we have an integral. So let's take a look at this. So you have this Gaussian reverse kernel. You integrate this over all possible WT. So WT is it lives in Rn, but you integrate this over all possible WT for which the argmax corresponds to ZT, right? So that's the first thing. And the second thing is, like there's some scaling factor because this integral at the top does not necessarily correspond to a valid PMF. So that's why you have a scaling term. And this integral effectively will give you a distribution over WS. And then you apply the argmax push forward to the distribution over WS to get a distribution over ZS. So in summary, you're given some ZT. You perform some integral over WT to get a distribution over WS. And then you apply the argmax push forward to get the distribution over ZS. And again, like in the paper, we provide a closed form derivation for this equation. Okay. And the final and the most important part is the likelihood. So these are like, okay, so the uniform state discrete diffusion and the Gaussian diffusion are two separate processes, right? And the only thing relating them is the argmax push forward, that is their marginals align. Okay, so now because these are two very distinct reverse processes, they induce different likelihood on the training data. Okay, so in the paper, we show that the likelihood for the discrete diffusion process is always higher than the likelihood of the Gaussian diffusion process, which means that it's always advantageous to design the denoising model in the discrete domain. Yeah, that is the only takeaway. And this is the reason why defining, like even though Gaussian diffusion supports all these interesting techniques, is well studied, especially when it comes to modeling one-hot vectors, Gaussian diffusion is not a good choice. And that is the only takeaway from this particular slide. right? And okay, so on this note, I'd like to have like Justin take over. He's going to present faster training, and after this, Zhihan will be presenting faster inference. Okay, seems like do you have a question or?
I think it's yes, we have a question.
Hi. Yeah.
Feel free to unmute yourself.
Yeah, can I ask?
Of course, of course.
Yeah. So I had a question on the motivation part where you mentioned that as mass diffusion models do not have the ability to self-refine, and that's
Yeah.
where USDMs come in, right? So in some of your works, you have also proposed remasking
Yeah.
strategies for discrete mass diffusion.
Yeah.
So can you comment on like why remasking mass diffusion might not be the best thing and why USDMs might be a better solution for that?
Yes. No, that's a beautiful question, and I'm glad you asked that question. So our goal is to perform few-step generation, right? That is, how do I generate 1,000 tokens in 10 steps? But the moment you perform remasking, you're essentially increasing the number of sampling steps because every time you remask a token, you would need to predict more, you need to perform more steps of denoising. And that sort of doesn't support what you were trying to achieve here. So the only reason I say uniform state diffusion is better than mass diffusion with remasking is because we want few step generation. And with remasking, you would end up increasing the number of steps of generation.
The way we obtain this one hot vector is that first we apply a Gaussian diffusion. So we have the one hot vector representing the, for example, cat, so XL, and we inject Gaussian noise in all the entries. Then we take the argmax, and that gives us this one hot vector over the word bat. Now, as you might know maybe from previous work, or you can also think about intuitively, if you take a softmax instead of the argmax, and you use a temperature parameter denoted here by tau, if you let this temperature go to 0, then that will make your softmax very sharp, and only the largest value will be non-zero if you let tau go to 0. Now, what we have observed in this work is that if you replace the argmax by a softmax, what happens with a non-zero temperature, what happens is that multiple entries will be non-zero. And one way that you can think about this is that you have a superposition of the clean token, in this case cat, and noisy token. So like this, instead of having a one hot vector, you have a vector still of the same shape, but where many entries are non-zero, including most likely both the clean cat and some other noisy token, here bat, that we show on this vector. And now you might wonder, okay, what do we do now with this large high dimensional vector? We cannot perform directly a lookup because it's not a single, there's not a single position that's equal to 1. So instead of doing a hard lookup where we select a single embedding, we perform a linear combination. So you can imagine that you have your representation for every token, and we compute a linear combination of all of these vectors, and the weight the weight that's associated with every vector correspond to the to the value in this vector that's obtained through first performing Gaussian diffusion and then applying a softmax. So we can see this bidirectional transformer. Before, it was taking it was always taking as input an integer and a time step, and then it was trained to predict a distribution of the word in the vocabulary. Now here we have our transformer that can take as input either the discrete values as before when we take the argmax, or it can take also this superposition of clean and noisy tokens that we see on this slide. And when we receive this superposition, we compute a linear combination of all the embeddings. Now we perform this operation at every position in the sentence.
Sorry. One quick question, Justin. Just so that one clarification question here. So you're saying earlier, you're typically in transformers, they see these words, and the very first layer of the transformer is the lookup, right? Like the transformer sees the word cat, you perform a vocabulary lookup, which gives you an embedding for the word cat, and then you perform the forward pass, the attention, whatever, right? And then you get the final logit. So what you're proposing is, instead of performing a lookup corresponding to the word, you have a vector as shown in this slide, and that you perform a weighted combination of all the embeddings. And then you perform the forward pass, right? Like, just so that we're clear.
Yeah, exactly.
Great.
Yeah. So this process, we apply it at every position in the sequence. So at every position, we get this distribution over the words that are used to compute the combination of embeddings. And now you might be wondering, okay, what happens when you do that? And so what we do in practice is we train with the objective that we presented before. So this the training objective that allows the model to learn to recover the true data and maximize the likelihood. And instead of feeding the denoiser here x theta, the argmax of omega of wt. So instead of feeding the zt latent, so the one hot latent, we feed this latent with this superposition of noisy and clean tokens that we just saw on the previous slide. And now you might wonder, okay, what happens when you do this? And because you're not really optimizing, this is not the true thing that you would like to optimize, right? It's not the true likelihood that you would like to optimize from that what the theory tells you. And so what we observed is that when we perform this operation early in the training, so let's say if we train for 1 million step, we perform this for the first half, so the first 500,000 steps, we are optimizing effectively a biased objective, because if you think about it, your model at each position is getting a combination of some clean, the representation of the clean token and the representation of the other tokens. So it gets some information about what is the true value that it needs to predict. But in practice, this is not what you want to do. So this is a biased estimation of your true objective. However, we observed in practice that when we use a temperature of, let's say, 1e minus 3, that the variance of the gradient, so if you look at your gradients during optimization, the variance of the gradient is much lower if you train with this linear combination compared to training with the true with the purely discrete latent, so ZT. And so as a solution, we propose during the first half of training to train with this biased objective, because it leads to a lower variance. And once the model has converged already to a certain level, then when we see that the loss is relatively stable, we change to use the true likelihood, where instead of using the softmax, we use the argmax and recover the regular training of uniform state diffusion. Because in the end, we want to maximize the true likelihood without this bias that is very helpful during the early stage of training, but ultimately that's not the end task that you want to train for. So when we talk here in this slide about 2 times faster training with curriculum learning, we observed that after 0.5 million steps, we were achieving better numbers or better validation perplexity than previous uniform state diffusion. Even though we were training still with this curriculum, we already beat the previous work. And when we further remove the curriculum for the second half of training, we reach even better number, which I will show now. So let's talk now more about the results, now that we have discussed how to train faster. So the most standard way to compare those language models is to use the validation perplexity, so to estimate how well the model predicts unseen data. And we observed that with this curriculum learning strategy that we presented, our model Duo achieves better validation perplexity than the prior work, so SED and UDLM. And we approach the performance of MDLM, which is a masked diffusion language model. Furthermore, we can evaluate the perplexity on unseen data, so other data set that the model has not been trained on. It is also a common task that is often reported in discrete diffusion papers. And we found that Duo on 3 out of 7 tasks, so on 3 out of 7 unseen data set, was performing better in a zero-shot perplexity evaluation than the autoregressive model, which is quite an achievement. Finally, so this is a new result that we haven't really, that was not part of the original Duo paper, but part of some further work to be discussed probably at a later date, where we look at what happens when you scale the Duo model that we have presented now on likelihood. What happens when you try to scale it to much larger size than typically seen in discrete diffusion papers. So this is quite standard in autoregressive model to perform some scaling law analysis. And for people unfamiliar, I will give maybe a small introduction of how we do this. So first, on the left, you have isoflop curves. The isoflop curves are obtained by selecting a certain training budget. So in the legend, you can see a certain budget for the number of floating point operation that we allow for training. And for this budget, we train a few models with varying model size. As you can imagine, a model that's much bigger, if we have a fixed budget, is trained for fewer steps. And then, given all of this model, we can see that there is kind of a quadratic relationship in the log space. And so we can try to fit these points that we observe with a quadratic equation, and that allows us to find what is the optimal model size for a given compute budget during training. Now, once we have found this optimal performance for a certain compute budget, we can compare different model architectures. So in this case, Duo, MDLM, esoteric language model that Zhihan presented a few weeks ago, and autoregressive model. So for all of this model, we perform this analysis that you see in the first plot on the left. We train multiple models for every budget, and we look at what is the best validation perplexity that we can obtain for a given training cost, and that gives us this curve, likelihood versus flops, the second figure that we see in this slide. We can also plot the optimal parameters versus flops, so like given a certain training budget that you have, how big should be your model, and different model achieve different curves. Now, if we just look at this, we can think, okay, it seems that clearly autoregressive is much better at like lowering the likelihood compared to discrete diffusion, and that maybe MDLM also is better than Duo and esoteric language models.
One question, Justin. So let's look at the likelihood versus flops curve, right? So, okay, on the y-axis, you have the validation loss. X-axis, you have the training flops. What we observe is for any given flop budget, any point on the x-axis, AR gets a lower number than MDLM, which gets a lower number than Duo, which is the pink curve, right? I also like, could you enable the red pointer so that it's easier to see? Like if you go to the bottom left, Justin, if you go to the bottom left of your presentation.
Oops.
Okay, I don't like.
Wait, yeah.
Okay, let's go to slideshow. Yes, let's go to slideshow. Now go to bottom left of the hover over bottom left of the screen, and then you'll see the red pointer.
Right. Yes.
Nice. Yeah. Great. Okay, so what I was trying to say is, like for any given point on the x-axis, we see that AR gets a lower number than MDLM, which gets a lower number than Duo. And if we were to compare, like from the paper, MDLM requires about 13x more flops. Okay. Yeah, MDLM requires 13x more flops to match the validation loss of the AR model, and that the Duo model probably requires, do you remember the exact number? Was it like 25, 26x more?
I think 23 or 25, yeah.
23 or 25? Okay, more flops, right? So Okay, so that's the takeaway. So you're saying the takeaway is that Duo requires more flops to match the perplexity of the MDLM model or even the AR model, right? And okay, all right. And then on the rightmost plot, we have the speed quality Pareto frontier. Yeah, you might wanna. So do you mind explaining what that plot is?
Sure. So
Yes.
as we were saying, like if we just look at those plots in the middle, you might conclude that maybe you should just train an autoregressive model because it reaches a better validation loss. However, by just looking at the likelihood, it doesn't tell the whole story because it just tells you how well it can predict the validation set, but it doesn't tell you what happens during sampling because, for example, with an autoregressive model, you need to predict one token at a time. So even though you might have the highest quality predictions, during inference, it will be also very slow. So that's why it's also important to look at what happens when you try to sample new data. And on the rightmost figure, we see that we are showing for a given throughput. So we have still our 4 model classes: autoregressive, duo, esoteric language model, and MDLM. For a given throughput, we look at what is for a given generative perplexity, we look over all of the models that we've trained before, what is the fastest model that we can find in each class. So for example, let's say I have generative perplexity 60. We try to find what is the fastest autoregressive model that reaches a generative perplexity. So the generative perplexity, for people unfamiliar, is a measure of the quality of generated text. So we use a larger model to compute this metric based on the samples. But basically, that's what to obtain the sample, we look at the different generative perplexity that we would like to achieve, and we pick the fastest autoregressive model. And so we do that for every model class. And if we look at this, it tells a different story compared to the likelihood only plots. For example, here we see that MDLM, which on the previous plot you could conclude is better than Duo at every compute budget. We find that in terms of sampling speed, the Duo model achieves better generative perplexity than the MDLM for every throughput that you would like to achieve. And we can then compare again with autoregressive. Autoregressive models still achieve the best quality. However, they are also the slowest. And as we can see here, if we want to achieve the best performance versus throughput trade-off, for this region here, we should use mostly a Duo model. And if we want very high throughput, again, the Duo model dominates. And for a slight window in the middle here, the esoteric language model dominates the generative perplexity versus throughput Pareto frontier.
Okay, so one clarification. So I think you've done a great job in explaining the plot. Just to reiterate what Justin said was, okay, we want to study how sampling speed relates with sampling quality, right? So on the x-axis we have throughput. A higher number means better, and on the y-axis we have generative perplexity. A lower number means higher quality samples. So naturally we want to be in the bottom right part, of the curve. So there are a couple of ways to study, like, well, one can train just one model and just, vary the number of sampling steps in diffusion language models. But for autoregressive models, one can do numerous things, like you can train models of varying sizes, right? So for this experiment, we train models of varying sizes for the AR model, for the Duo model, and also for the MDLM model, right? And for AR model, so that's how we get the Pareto frontier for the AR models, because every model is different size. So every model has a different throughput and sample quality associated with it. Okay. Now for the diffusion LLMs, MDLM, Duo, and SLMs, we vary the model size and also the number of sampling steps. So if you have you can imagine, if you have a bigger transformer, you can take fewer. You can make fewer denoising steps. And if you have a smaller model, you can make more number of denoising steps to maintain the similar throughput value, right? So for every given point here, we take an we report the maximum throughput that that you can achieve with varying model sizes and varying the number of samples, right? So let's say generative perplexity of 120. So for the Duo model, let's say we have 5 different models. For the sample quality, now the question is, what throughput do we report for the sample quality of 120? So we have 5 different models. You sort of tweak the number of sampling steps for every model, and you report the highest possible throughput for that, right? And we do that for MDLM, Duo, and SLMs, get the Pareto frontier. And the takeaway is that AR dominates when you can tolerate source sampling speed. And the moment you want higher throughput, Duo dominates in a certain range and SLMs dominates in a certain range. And that's it. Okay, right. Now we can move on to the next slide.
Yeah, thanks for the discussion, yes. And finally, so in addition to the likelihood and the generative perplexity, we can look at some downstream tasks. So you might have seen this paper on Twitter recently that perplexity cannot always tell right from wrong. And basically it shows that mostly as you scale the sequence length, maybe the perplexity might not be the best measure of sample quality, because if your model finds one very high quality sentence, in this work they show how you could find also another very bad quality sentence where your model would for which your model would assign a low perplexity as well. And so as such, it's also important to look at actual downstream tasks. And in this work, we also look at what happens on the GSM-8K dataset, which is I think, high school or maybe middle school even math problems. And that has been also studied in many autoregressive model paper and also mask diffusion paper. Most importantly, this scaling up mask diffusion model on text paper, which was accepted at ICLR last year, and that we show here in this table as prior worked SMDM1B. And so what we do to understand what happens with scaled up Duo is that we perform the same supervised fine-tuning recipe as them. So the most important part is that we get those those problems that are that are made of a prefix that contains the problem description, and then you have some thought that most of the time rewrites the problem into mathematical formulas, like in terms of addition, multiplications, and then you have the answer. So we fine-tune the Duo model, the MDL model, SOLM, and autoregressive model on this data set. And then we perform one by one decoding, so one token at a time, left to right, to follow this recipe from this prior work. And interestingly, we find that Duo outperforms MDLM and AR when trained with the same data mixture, with the same budget, so in very similar conditions. So that was quite an interesting result.
Yes, and then one other thing was that Justin mentioned we perform left-right decode. So in GSM-8K, you have a prompt, and then you have to generate the reasoning trace, and then the final answer, right? So, so in the prior work, SMDM or even like LADA, they propose this confidence based on masking strategy. And when you look at, which means that you, at any given denoising step, you decode tokens where the model is the most confident, right? And when you look at the generation scheme, it just so happens that that kind of sampling strategy corresponds to left to right decoding strategy, and it's like one token at a time for the most part, right? For those reasons, and also like in reasoning, when you think about it, when you're trying to generate the chain of thought, if you make any error in the initial stages of your chain of thought, the later generation is going to be garbage, right? So for those reasons, we perform SFT on all these models, and during generation, we only sample in a left to right fashion for Duo, SOLMs, and MDLM. What we see is MDLM sort of like is almost as good as AR, but slightly worse. SOLMs is way off. But again, like the main strength of SOLMs is KV caching, which is not present in any other methods. In MDLM, you can do it through blot diffusion, but also it's not very effective, as we showed in the SOLMs paper, right? But with Duo, we see that when you perform left-right decoding, we get better GSM-8K numbers than the AR model. Now, are we trying to make a statement that Duo is strictly better than AR? Definitely not. But again, like in this paper, we only performed the reasoning experiments on GSM-8K. What we did not do was run coding related experiments or run experiments on Math 500 or more complex data sets. But nevertheless, at 2 billion scale and the pre-training data that we had only allowed us to run experiments on GSM-8K. And with that, we get this number, which is pretty promising. Okay. Right. I'll let you take over just. Oh, okay. So I guess like now Zhihan will take over and present faster inference.
Yeah, great. So now let's explore discrete consistency distillation that's proposed in this paper that enables drastically faster inference. So diffusion sampling requires many steps that iteratively refine a sample from the prior distribution into a sample from the data distribution. And the goal of distillation is to enable few step generation that yields samples of similar quality. And one powerful class of distillation methods is called consistency distillation. This relies on the existence of these deterministic probability flow ODE or PFODE mapping from points under the prior to points under the data distribution. However, PFODEs only exist for Gaussian diffusion, but not for discrete diffusion. And motivated by this discrepancy, the duality paper presents discrete consistency distillation, or DCD, a technique for distilling uniform state discrete diffusion by leveraging the PFODE of the underlying Gaussian distribution. Let's see how DCD works. So given a Gaussian random variable W1 from the prior,
deterministic mapping from the prior to X using your denoising model X theta, right? Like the one that you showed in the previous slide. But here, we sort of construct this deterministic mapping in a different way because we do not have a denoising model that is defined on the Gaussian latents. Recall that at the end of the day, we trained a discrete diffusion model that is defined on the discrete latents. And because we do not have the Gaussian denoiser, what we say is, let's just construct this deterministic mapping using this formula at the bottom. So the formula at the bottom is essentially the DDIM sampler. I mean, if you rewrite the equations in the DDIM sampler for the variance preserving Gaussian diffusion process, that is the equation you end up with. But anyway, thought I should just have this comment, but take over, Zhihan. Sorry to interrupt.
Yeah, it's all good. Yeah, so to actually perform the distillation, we pick two Gaussian latents at time step S and time step T. And then we apply argmax operation to these two Gaussian latents to obtain the corresponding discrete vectors z sub s and z sub t. And then we have a teacher model with frozen weights that sees the less noisy version of x, which is z sub s. And the student model here sees a noisier version of the data, z sub t, and is trained to match the predictions of the frozen teacher using the KL loss shown at the top. And in practice, we perform multiple rounds of distillation with progressively larger step sizes. So at the beginning of distillation, both the teacher and the student models are initialized with the same weights, but the teacher's weights are frozen. And then after every round, the student becomes the teacher. So we can do multiple rounds, round 1, 2, and so on. And in the paper, 5 rounds of distillation were performed in total. And in the extreme case, the student model is forced to predict the clean sequence in a single step.
Oh, one quick question. So do you remember how many gradient updates we performed for every round of distillation?
I think it was
10,000?
10K, yeah.
10K? Oh, okay, nice. Okay, and then one final question. So you have this scale, right, between x theta and x theta minus. So, okay, so you're showing this for, so ZT is supposed to be, like a sequence, but here you're assuming ZT is a single word. And okay, so x theta ZT comma T is a PMF, is a probability distribution over X. So X is a one-hot vector, X theta is a PMF, and that allows you to construct the KLOS. Okay, cool. Anyway, never mind. Thought I did just.
Yeah, no, that's right. Yeah, so like all the previous notation, like for simplicity, we're with respect to a single token, and this notation can be easily adapted to sequences as well. Yeah, and now let's look at the distillation results. So this is a complicated diagram, but plot, but let's go through it one step at a time. So on the x-axis, we have the number of sampling steps. The lower the better. And on the y-axis, we have generative perplexity, or GenPPL, which is a measure of sample quality evaluated under a bigger autoregressive model. And it is the lower the better. And let's look at the methods here. So we have the orange dashed line reporting MDLM numbers. And we see that is probably the worst among all the things plotted here because it has higher GenPPL compared to other methods at every sampling step. And notice that we have these smaller font, numbers with smaller font. And basically, these report something called entropy. And it is high if the bag of tokens created from the samples is diverse. So it does not care about the relative order of the tokens, just whether your samples represent a large unique set of tokens. And then in the blue dashed line, we have dual, and we see that it's better than MDLM at every sampling budget with a marginally lower entropy. And in the brown line, we have MDLM with SDTT. So this is the method, the distillation method for MDLM proposed in Justin's paper at iClear 2025. And we see that it is drastically better than MDLM. And with a high number of sampling steps, we see that it approaches autoregressive quality denoted by this red line here. And then let's look at the dual with DCD. We see that it outperforms MDLM with distillation at low number of sampling steps, but is outperformed by distilled MDLM at high number of sampling steps. However, with the greedy tail sampler proposed in the duality paper, we're able to get even better quality from the distilled dual. And in particular, we see that it outperforms distilled MDLM at low number of sampling steps and is on par with distilled MDLM and AR at high number of sampling steps.
Do you have any comments on the greedy tail sampler, what that is or how it works?
Yes, it's coming up in the later slides. Yeah, so to highlight the effectiveness of DCD, so we want to focus on just a few numbers here. We see that the distilled model successfully reduces sampling steps from 1,024 under the base model to just 16 steps without any loss in quality measured by GenPPL and diversity, which is measured by entropy. And so the reason why we report entropy is because GenPPL can be gained by producing degenerate samples. So we want to compare the sample entropy just to make sure. And for the extreme case of generating 1,024 tokens in just 8 steps, we use the greedy tail sampler proposed in the paper, which performs ancestral sampling up to the final denoising step, followed by one final step of greedy decoding. And with minimal entropy loss, this approach achieves around 100 times faster sampling compared to the base model.
Zhihan, what about the greedy tail sampler again? What is it? As in, like, can you explain how it works?
No. Yeah, so basically if we look at the yellow, like this orange bar here, it's basically numbers obtained by ancestral sampling. And this maroon colored bar is produced by the greedy tail sampler. And basically the greedy tail sampler is you perform ancestral sampling up until the final denoising step. And you follow that with one extra step of greedy decoding.
I see. And then also, like, can we go back to the slide comparing GenPPL and sampling steps? Okay, so I have one question for you. How do you okay, if I were to look at GenPPL at 1024 sampling steps for Duo with DCD, MDLM, DCD, and AR, they sort of converge to one number, pretty much the same number, right? So do you have any comments on that, or?
Yeah, so they do converge to similar numbers under GenPPL. But as we can see that for the autoregressive samples, they're better in the sense that they're more diverse, which is indicated by this higher entropy number than all the other points that's converging here. And we see that for dual, distilled dual, with greedy tail sampler, it sort of gets the worst entropy, but 5.2 compared to 5.6, that is a drop, but it's a very minimal drop.
Okay.
Yeah.
Thank you. All right. Cool. Let's. Yeah, I'll let you. Do you have? Okay. Wait. So is it my? Okay. So the conclusion in the future works, right? Okay, give me one moment. Let me try to share my screen. Okay, you can see my screen, right? Okay, yes. So to conclude this talk, we discussed how in this duality paper we enriched the design space of uniform state diffusion models with Gaussian diffusion, and we leverage this connection to design a faster training algorithm for uniform state diffusion and a faster sampling algorithm where we obtain about 2 orders of magnitude speed up with minimal hit on sample quality. And I think the main contribution of the paper is that it opens the doors to map all the techniques that exist in Gaussian diffusion to the discrete domain. It is not very straightforward, but at least we show the way. Like, we have all the right equations. It's a matter of just figuring it out, like how to use those equations to unlock even more techniques in the discrete domain. Okay, now feature works, very important. The very first thing is classifier-based guidance, right? So if you see here, typically in classifier-based guidance, you have a trained discrete diffusion model, and you have some classifier that evaluates the sample quality. Imagine this: you have a discrete diffusion model produced that tries to predict the molecules, and during inference, you would like to generate molecules with certain attributes. The way you would do this, you do guidance during generation, is you sample from the model, and during the course of generation, you evaluate every intermediate sample, let's say ZT. You feed it into a classifier, get some gradients of the final reward with respect to the sample ZT, and then you use that gradient information to steer your generation towards more desirable samples, right? So that's how classifier-based guidance works. And all the current methods, they apply the gradient to the denoising function p theta s given t. And what happens is, especially in the discrete domain, in Gaussian diffusion, when you perform classifier-based guidance, the gradient information sort of accumulate. So there's a very smooth steering towards the target. But in the discrete domain, there's a discretization step as you go from ZT to ZS, right? ZT is discrete, you have a distribution. You modify the distribution to incorporate the classified gradients, and then you sample from that distribution. So that sampling process part is discrete, and you end up losing, have this accumulation of gradients as it happens in Gaussian diffusion. So what I'm proposing is very simple. Try to add classifier gradient to the Gaussian latent WT instead of adding it to the discrete distribution. You add it to the Gaussian latent. And what, again, like at the end of the day, we want to restrict ourselves to the discrete domain because we have improved likelihood there, right? So at the end of the day, we still want to sample using the discrete diffusion, but I'm asking you to modify the p theta s given t distribution. And that way, you have this continuous latent where the gradients accumulate over time, and you use this equation to sample in the discretes. So that's number one. And the second thing is, again, like this equation that we saw earlier in the talk, sort of allows you to define the reverse process in the discrete diffusion space using the Gaussian denoiser, which means that one can also think of employing all the parameterizations that exist for the Gaussian diffusion models, right? And so effectively, you would design a denoising model for the Gaussian latents, use that denoising model to define your discrete diffusion denoising model, and train the model with the discrete elbow. Yeah, and this is not very straightforward because defining your discrete diffusion model in terms of the Gaussian diffusion process involves an integral. This is intractable, but there are numerous Monte Carlo methods that one might try that I personally did not get a chance to look into. So you should definitely look into it. And right at the time of speaking, there are no other, mean parameterization is the standard way to parameterize denoising models. And if you can write any papers here, it'll get a lot of traction, and hopefully it'll also improve the performance of these models. Okay, yeah, I think that's the end of the talk. Thank you so much, Justin and Zhihan, for co-presenting this with me. And now I would like to take questions. Okay, so when I look at chat, so I believe Gavia has some questions. I would I think it's better if I just ask him to ask it in here. Okay, all right, Tejumai.
Okay, I guess I could. I was just asking about the objective. I mean,
okay.
The conclusion is just that I'm confused. So I don't have a clear question anymore. I've asked my questions in the chat.
Okay, so let me take a look at the chat. Okay, let's turn off most. We're going to do a bit of temp conditioning. Oh, sorry, no, this is a different person to work in Gaussian space where your targets are not one-hot vectors, because then you use, okay, I guess it'll do the expression in the hyper Gaussian space if you're using category. Maybe it's going to decompute it. Oh, so you're asking how we compute the gradient during training of the curriculum learning phase? Is that the question? Or
more just which objective you're computing a gradient of. It sounds like you are computing a gradient of a discrete diffusion objective at some point. But reading the paper, I thought there was some use of a continuous objective, because then you wanted to use continuous diffusion methods, which rely on having that continuous space. But it seems like it's a little more complicated than that.
Oh, sorry, just so that I understand the question properly, are you asking if we train the model with a continuous objective, or if I tried training the model with continuous objective, or if that helped, or is that, sorry, I just want to make sure I understand the question.
No, my initial confusion was I thought the model was trained on a continuous objective, like you were just taking a one-hot vector and then regressing towards that one-hot vector as a diffusion model. And I had some qualms about that might induce bad calibration, and asking whether you measured any probability calibration experiments on the training set.
Okay. Oh, I see. Yes. So a couple of things, right? So as you mentioned, we trained even when the input to the model is Gaussian latent with a softmax, we train it with the discrete diffusion elbow. So the only thing that changes is what the denoising transformer sees, right? Okay. Now, does it lead to? Is there any misalignment between? Does it lead to any misalignments? Yes, because your model is trained on Gaussian latents or like this real value latents, and when you measure the true perplexity of the model, you require discrete latents, right? So when you evaluate the perplexity of the model in the correct manner, it definitely performs worse than the model you would get if you trained it with the discrete latents. Now, so what we do is after we train the model, like if you can see the screen, like to 1.5 million steps. After 0.5 million steps, the moment we start training or fine tuning the model with the true diffusion elbow, we get a better likelihood than the model that was only trained with the elbow, right? So there was some misalignment. There is definitely some misalignment during the curriculum learning phase, but once we switch it off, we get a model that is much better than the model that was only trained on the elbow. I hope that answers the question.
Yeah, I guess a little. I guess we'll have to take some.
Okay, yeah, like also like we're happy to take any questions on Discord like after the talk. So feel free to shoot any questions, and I'm happy to answer them later. Okay, all right. Okay, so okay, Tejo, do you have a question? I know you're raising your hand, so.
Yeah. So I wanted to ask like the work on basically MDLMs that was done by Justin, I think it is called SDTT, and this work on consistency distillation for USDMs, I think both are kind of trying to solve a similar problem of predicting multiple tokens at the same time. But then intuitively, what do you think? USDMs in USDMs, it seems to work better. So why compared to MDLMs? So why do you think in USDMs this distillation is working much better in terms of enabling the prediction of multiple tokens at the same time compared to MDLMs?
Yeah, I mean, I think in the beginning of the talk, right, the main motivation behind this work was mass diffusion models cannot update a predicted token, especially in the low sampling steps regime, where we do not have the flexibility of remasking the tokens because we don't want to increase the number of NFTs, right? But for USDMs, these support self-correction. So self-correction is the main reason why USDMs are so amenable to distillation.
I see. So just a follow-up. In terms of like, let's say we talk about just a single step generation, I think like then both of them should be in some sense similar, but it seems that USDM is doing better.
Yeah, so a great question, right? So when you think of single step generation in MDLM, you're trying to your input is deterministic, that is a sequence of all mass tokens, and it is trying to map the data distribution, right? So it's a one-to-many problem, which is almost impossible. Like unless you change the factorization, like MDLM models every token independently. Unless you do something to that, there is no way MDLM can map the entire training data distribution. But in USDMs, your input is stochastic, where so there's this hope that like it's a many-to-many problem. So that's why there's a hope that USDM is more suitable for single step generation than MDLM, which definitely cannot do that. Unless, again, probably if you come up with some interesting factorization of the output of the mass diffusion model, there's just like no way it can happen. So I hope.
Yeah. Thank you. Thank you for answering.
Okay, so all right, I'll try to take questions from the chat. Okay, Gabia, we're done. Again, in the time conditioning did not seem to help much, and I think. Okay, I believe David's question was answered. Yeah, in MDLM, the model can infer the amount of the amount of noise level through the number of mass tokens, but in uniform state diffusion, everything is clean, so it's much harder. And explicitly specifying the corruption level through the time conditioning seems to help. It's more of an empirical finding than theoretical. So, okay. Consider less interruptions or clarifications in the future. Okay, I will take that into account. Okay, do you think the future of discrete diffusion is? Yeah, it is mostly uniform. I think in the next few months we'll have a flurry of papers where we'll show that uniform state diffusion surpasses mass diffusion. It is like inevitable, and it's it is going to happen at least. Like next week, I believe Justin will release his paper, the follow-up of the duality paper, Diffusion Duality Chapter 2, where he'll share a lot of interesting findings about how uniform state diffusion is better at text generation and image generation. And a few months later, I have plans of releasing bigger diffusion language models as well at 80 billion scale, or maybe 400 billion scale. So it'll be uniform state based. So yeah. Okay, and so I was having distillation. Latent shadows, the Gaussian on the same line of thought. Oh, I don't know if that paper. It's interesting. I'll look it up. Latent shadows. Huh. Interesting. Okay. All right. So, do we have any questions, or can we end the talk right now? Okay. Seems like we can end the talk now. Thank you, everybody, for showing up, and thank you for all the great questions. Yeah. I guess we'll see you next week. Right.